So welcome to the pre-recording of lecture 27 in the 8-week summer course, MCS 260, Introduction to Computer Science. So this is the first part of session 14, scheduled for the end of the 5th week in the 8-week summer session. So we started in the last lecture, the second part of session 13, with the introduction of object-oriented programming, object-oriented design and object-oriented programming. This is a technique to look at programs in the large, but it also is a method that allows us to extend the existing range of data types. So we can look at making classes as defining our own types. So in this lecture, I will essentially give two illustrations of applications of making our own types, and I'm doing this in the context of operators. Operators to compute and to compare data. All right, so this is a mathematical computer science class. Let's look at computations. When one thinks about running algorithms, you think about the resources it will require. In scientific computing, not only numerical analysis, but in scientific computing in general, one often talks about flop. Flop is a floating point operation, and flops is in this lecture the plural of flop, of one flop, one floating point operation. But it also flops also means the number of floating point operations that the program does per second. So here we will use this word flops simply as the plural for floating point operations. Historically, so MATLAB is a frequently used program in scientific computing. MATLAB actually had a flops command. So at the end of a computation, you could ask MATLAB how many floating point operations were performed. And that was a very useful utility in the investigation of the algorithms. What I want to illustrate here is that with object-oriented programming, you can actually reintroduce this flops command, where we are going to extend the data that we maintain. So every object of the class flop float will be a float, and that's a floating point number. And then we will have an integer number that counts the number of operations that went into the computation of that number. So in some sense, with every floating point number that we work with, we have kind of a weight, or if you like, perhaps better, the cost, the computational cost that it took to get to that number. Now that's it. So you can do this in Python, pure Python without any classes, if you would store a tuple. But then the multiplication and all the arithmetical operations would become extremely cumbersome. So we can redefine our own, we can actually define our own plus operations. So that's actually the main point. We can overload the plus. And we have already seen several instances in this. So there is the plus on strings, which is the string concatenation. So it's not adding up numbers. No, it's just concatenating them. In a very similar way, you can join two lists. So you can take the sum of two lists, which will just append all the elements of the second operand to the first operand. Notice that these type of pluses are not commutative in general. If you add AB plus BC, then you get something different when you swap the operators. Now on lists, so there is the class list. The list actually has defined this plus operator via the underscore underscore add underscore underscore. So if you on any class, we have seen the underscore underscore init underscore underscore and also the string method. So these are two methods that we always define. But you can also define the plus on your objects whenever you feel that there is a need for it, and you can give meaning to this type of operation. Here are the comparison methods. So it is important that we define when things are equal. So in some sense, if the we've encountered this problem already with lists. So lists are essentially references to sequences. So you can have that the references are the same, and then also they refer to the same object. But you can have two different lists that have the same content, but they are different as objects. Here in our application, we want to compare a flop float with a float. So we have to, so we can of course always compare, but no matter what the float will be, even if the float will be the actual floating point value of our flop float, we will always get false. And what we actually want is that when we compare a flop float with a float, that actually these two numbers are the same. We can not only redefine, I speak about redefining, the proper terminology is overriding. So if you don't do anything, then Python will just compare the objects, and it is not entirely wrong, but it's actually not the meaning that we want to associate to the equality. So we can likewise also define all the other comparison operators. So here is the notation that we use for the operator when we apply the operator. The method that corresponds with this are these built-in methods. So they have these double underscores when you define them. Likewise, so here is the whole list of available operators. So we have the all the arithmetical operators, the addition, subtraction, multiplication, and division. But then you also have the in place methods, and which are just a shorthand. If you increment, say, a counter, you can write it shorter as the plus equals. Um, that's not so important. What I will spend some time on is the reflected addition and the reflected operators. We will need to define them if we want to add to a float a flop float. So this is to assume that with the add we can define the addition of a flop float as first operand, and the second operand is then a float. But how do we do it in the other way around? So for now this is too detailed, but here is I wanted to be um, extensive, complete. You also see the invert operator. So when we started using Python as a calculator, I could have provided this whole list of operators as well. All right, here is the reflected addition. So when we actually write plus, we actually apply the add operator to the first operand. So x dot underscore underscore add underscore underscore y. this works when the first operand is a flop float. And there is also the self and the other that we will see. So we have introduced a keyword self. So self is a reserved word. So as a programmer, you have to refer to it when you define methods. In binary operations, such as the AND, we have the self, which is the first operand. Then we have the other, the second operand. So we are using the reflective add when we are adding to a float a flop float. So this is not such a great slide, but I hope that the Jupyter Lab and the code that I will be showing will make that clear. Okay, so that was our first application. The second application concerns the hypercomplex numbers, or just the quaternions. In calculus, in multivariate calculus, we are working with three-dimensional vectors, and the basis vectors are then also denoted with these letters I, J, and K. So the I typically stands for the imaginary unit of the complex numbers. In Python, the imaginary unit is actually denoted by J. So the symbols are a little bit, this is conform what electrical engineers do. So I will illustrate this. So the quaternions are extending the complex numbers. So they were introduced in the middle of the 19th century by the Irish mathematician Hamilton. And this was done before vector algebra was in use. They have applications still to computer graphics. So they can be used to represent rotations much more compact than you would do with matrices. So in some sense, this is mathematically probably too advanced for this course, but I just want to indicate computer graphics is another discipline where quaternions are being used. So instead of using a 3 by 3 matrix to represent a rotation, which are 9 floats, you only need 4 numbers if you work with a quaternion. So not only in computer graphics, this is used also in kinematics, in mechanical engineering. So there quaternions also appear. Um, Here is the rotation in space. So you rotate, when you rotate, you pick an axis and an angle. So this is already to indicate that 4 numbers suffice. So you can define a rotation by a vector, here the unit vector u, and then you have the angle theta. And the arithmetic with the quaternions is here given. It's here defined to represent that rotation. So the rotation is represented by a quaternion, and then the rotation is applied via these quaternion multiplications using the inverse of the quaternion and the point itself. So a quaternion has a conjugate, just like the complex conjugate, and it also has a magnitude. So there are some oddities about quaternion operations, but this is essentially the essence and the relevance for computer graphics and also for mechanical engineering. For the point of our course, object-oriented programming, and in particular with operator overloading, you see here we have these operators that are here written mathematically with these circled multiplication. I wanted to indicate that this multiplication is different. But because of the object-oriented nature, the right correct multiplication will be executed depending on the type of the operands. So you can define, and I will show you how to do this, we can define a multiplication on the quaternions. So if you have to use quaternions, it's not in Python, but it is in the symbolic uh, computer algebra. It's in SymPy, so in the computer algebra SymPy, which is a Python package. All right, here are then the exercises. So they are mainly concerning the class quaternion. So quaternions are actually very good practice because of all the operations, which are less trivial than the flop float. So the flop float is another illustration of a wrapping. So we actually are wrapping the floating point operations, extending them with the data attribute. Um, there is there was the class rational that I introduced last time. So with the rational class, when I defined object-oriented programming in the last lecture, I was indicating that the objects are central, not the algorithms. But the algorithms come in the methods. So in some sense, it should be very clear that object-oriented programming is another way of organizing your algorithms. We started out by describing our algorithms with um, control structures. Then we encapsulated them in functions, functions that belong to modules. Now we actually are reorganizing our algorithms into the methods of classes, the methods that are applied to objects. All right, so this exercise is important if you have started on the exercise for the rational class. And I was pointing there that the greatest common divisor is called when you are making a new natural number, a new rational number. Because 4 over 2, you want to normalize this as 2 comma 1. So 2 is the numerator, 1 is the denominator. So you are using the greatest common divisor to remove the common factors from the numerator and the denominator. So the algorithms are still very important, but they are organized differently. Um, Regarding again the concepts of design, so when you make a class, you have to do a lot more work. But if you are doing all the extra work to make your class as complete as possible, um, you can reuse that class. So it's obvious here from the quaternions that the work that is invested in building this abstraction will pay off for many applications. All right, let me then go to the Jupyter notebook that I have prepared. Um, So I will try to make this lecture as self-contained as possible. So we have, when we think about a class, we think about the data attributes first. So here I have not included any class diagrams, so but it could be a good exercise to actually draw a class diagram. Mainly also because from a perspective, we are not really thinking here about large programs. What we want to do is actually quite clear. So in some sense, I talked about algorithms. Here actually we are just redefining algorithms. So in some sense, we are defining the plus that stores more, that does more than the plus, that also keeps track of the number of arithmetical operations that have been used to um, to obtain the numbers. So when we add two flop floats, they both numbers have a cost. So we are adding up the values, um, and we are adding up also the costs, the flops, plus one, plus the extra operation. So that's the entire idea. What's the use of this? So the use of this is that your programs, uh, you don't, so there is dynamic typing. So at the time when a plus or any arithmetical operation is executed, Python will check the type of the operands and will apply the add method that we have defined on the flop float. Um, so I have organized there is this flop floats file. The flop floats file exports the class flop float. Um, this object is actually no longer necessary. Perhaps I should not have added this here. But you see the constructor. So the help actually shows how to make a flop float. There are two arguments. So in the constructor, you set the data attributes. There are default values. If flop float is called without any argument, then we get the zero number. So we can make a flop float with a particular value, and we can also indicate its costs. So the second argument, n, is the initial cost of the number. It could be that the number that we want to work with has already gone through a lot of operations. So a very similar result would be to do an automated error analysis. So in some sense, you can multiply the and you could have an extra attribute, but this would lead us too deep into numerical analysis. An extra attribute could be the the estimate for the error. There are also techniques of interval arithmetic where you can compute with a left bound and a right bound. But also this would lead us too far here. So there are many different kinds of arithmetic that you can define. Okay, what is important? So there is not only the self, but there is the other. I glossed over this, but if you look at, for example, the first operate methods that is defined here, we have the self. So this is the same self as when you run the constructor. That refers to the first operand in the addition operation. The second operand is referred to by this other. So when you define the addition, you don't really know what are the names of the first and the second operand. So in some sense, you can't really work with the arguments. Methods are very similar to functions. You can provide them with any arguments, but there's always the self for a method that is a member of the class. So we have the data attributes and also the functional attributes. When you have a function or a method, so you can, in any file, you can put functions in there, but as soon as there is a self, then it is a method that belongs to the class. So you see here that there is this init, so with the extra arguments. So last time we saw that you can define a constructor with optional arguments. Here we have default values. So there are optional arguments, keyword arguments, and default values. Okay, the other is important. Let me actually go to the class itself. So a class is stored in a file which is treated as a module. So there are two documentation strings here. So we have a description of the module, and then we have a documentation string of the flop float. So here I have the module called flop floats, and then I have the class flop float. And here you see that actually I have removed the object, but it shows up when the help is being done. So when these documentation strings are important to actually motivate and to describe what the code is supposed to be doing. So we have the data attributes that are defined um, when we construct, when we define the constructor. So here I'm doing the explicit uh, typecast. If the user wants to treat 3 as a flop float, then 3 will come in as an integer. And it should be really a float that I'm storing here. Float is perhaps not the best name. Float is also the name of the type. But within the context, it will be very clear. Whenever we have a variable, say x, we can do x dot float, x dot flops. So these are the two data attributes. So let me illustrate in the Jupyter notebook how this is used. So here I'm importing now from flop floats the class flop floats. So again, there are two words here. Flop float with the camel case. Pylint complains with this. Pylint is a style checking. So with Python, one prefers the snake style. No uppercase, but then underscores in between the words. The alternative is the camel case. Um, so I make a flop float, 3.1415 and then something else. You can see I have the x dot float and the x dot flops. I did not initialize the flops. Um, there are then the representations. So flop floats is again, it's the name of the class, but when you run it, it's the same as actually calling the constructor in it. So that's the code that is executed. We see that when we type X in a code cell, we see the representation of the object. That corresponds to the string method. The string returns a string, and it also corresponds to the print. So this is the way we have defined it. That's the way how it is defined in this class here. So we have the string representation, which allows to do another formatting. So I'm giving here the format string, so that will return the format with scientific notation 4 decimals after the dot. The representation is simply the string representation in its default form. So you could say by default we represent all our floats with in scientific notation and with 4 decimals after the dot. Okay, so we can extend this, so it's a little bit cumbersome to do here. And actually, the main point is actually that when we compute, so we can compute with a flop float. We can do the x times x. That will give indeed the square, but you see that the flops has increased. If I'm doing an addition, then the number of flops equals 2. This is the same as calling this add. Um, Now, let me now go to the definition of the addition. So here it is. So there is a self and an other because it's a binary operation. And I want to check if the other is actually also a flop float. So if it is, then I will add up the data fields and I will add up the flop counts. So I will make a new flop float with the sum of the two floats, and I will also adjust and I will set the second data attribute to the sum of the flop floats plus one addition that I did extra. Now, if that's the case when I'm adding up two flop floats, but in many programs you do not want to replace every constant with the making of a flop float. So we will leave our programs as they are. Um, so whenever there is an addition that is defined for a float plus something else, it will be executed. So the other can be just an integer. So that, as in the example. So it doesn't need to be a float, but it will count as a floating point operation. So there is the reflective add. The reflective add is actually just the same as the add. So I can actually simply define it with self plus other. So the self plus other will essentially uh, make sure that the add will be called and it will work. So this is necessary to do when you want to add as first operand first a constant. So there are a lot of words needed for very few code. So there is the in-place addition for brevity. It's actually the same. It's just a notational convention. Um, Sign flipping does not count as a flop. And then you see the symmetric. So just to make sure um, that that seeing a lot of examples helps. So then we have the minus instead of the plus. The multiplication is then similarly defined. Okay, so the other important issue was the equality test. So here you see the equality test. It is necessary. So let me first motivate it. What we have is that, so here we have the equality. If the equality would not be defined, then this test would always return false. And this is very strange. I mean, what we actually want is that we want that a constant number of a regular float is actually equal to a flop float if the constant, the regular float, equals the float data attribute of our flop float. Again, there's a lot of explanation, many words that need to be explained. So these things are different as objects, but the meaning, so in some sense this is true because we defined the equality operation like this. In the proper terms, we have overridden the definition of the equality operator. So that is done in the last element here. So this class is far from being complete. So the comparison operators, all the other comparison operators are not defined. So this will have only a limited use, but it will work, for example, for polynomials. So if you want to evaluate the cost of an evaluation of a polynomial, then this can actually be done. So the way I illustrate it here is with a summation of any number of random floats. So you can imagine that this would be here in a regular Python program. So this is a loop. The ransom is declared earlier as a flop float, but it could be in a function, could be in any piece of code. The Gauss is imported from random. It's a function that returns um, a random number following the normal distribution. Normal distribution here by default, 0 mean and 1 standard deviation. So what the value is for this sum of random numbers is not really relevant, but here you see that I'm doing 10 pluses, and at the end, when I'm executing this loop, I do have indeed that the value of flops equals 10. So one could have a very complicated function or a very complicated program just by letting your program run on flop floats. You will actually have an automated cost analysis without having to change the logic of your program. So you could still use the nice notation of your regular arithmetical operators. Okay, another illustration are the quaternions. I will be using the quaternions to illustrate the class-wide variables, but first the complex numbers. So there is the built-in complex type. And you can see if you do help complex, I don't need to import anything. You can see also the documentation string. So complex has a real and an imaginary part. And you can see here the notation J for the imaginary part. By default, if you want just to declare 0 as a complex number, you provide it with no arguments. Also, if you don't specify the imaginary unit, you have a real number. You have a 0 imaginary part. And here you see all the operations that are defined. So there is also the complex conjugate. The two data attributes are the real part and the imaginary part. You see the representation. So it's actually shown as a tuple. So there is this, indeed, you could say that in essence, all the data attributes in a class is in some sense another encapsulation over a tuple. You encapsulate the data attributes. Okay, so I mentioned SymPy during the slide presentation. If you're really interested in quaternions, then install the SymPy package and look how to work there with quaternions. It's not part of this course. I defined the quaternions simply because I wanted to have another example and I wanted to illustrate something about the class-wide attributes. The class itself is far from being complete. So you see the operations that are defined here. I have two class-wide, so here I can always get the documentation much quicker by printing the documentation string, as I do here. There's only one, and actually it's not a good documentation string. But I'm using it to illustrate two class-wide data attributes. So we have data attributes that are private for each and every object. Each and every object has these four components in a quaternion. It's extending the complex numbers. But then there is the class quaternion, which stores the count of quaternions, how many quaternions are already in use, and also the list of variables. We can store all the quaternions in a list. What actually happens is that we don't have an extra copy, but we have references. So who will actually store the list of all the quaternion variables. This is often very useful, that you can see the list of all the variables that are in use. Python has the globals, so in some sense Python has already there, but if you have with globals, you would have the all the variables that are defined in the current namespace. You would need to check the type of all the globals to select in the quaternions. Okay, so let me, in the remaining 5 minutes, let me show what is specific. So I have a good documentation string for the class quaternion. So also that documentation string I can actually print. So let me illustrate this. So there is the quaternion. Um, so Python is case sensitive. So there is the quaternion. So that's the name of the module. Also the name of the file. The name of the file is quaternion.py. So I will import quaternion, which is the name of the class, and let me print the documentation string of the class. So here you see the documentation string of the class. So observe that there are two quaternions. I could have used also a lowercase q for the name of the class. But I wanted to have a distinction between the quaternion, the name of the class, and the quaternion, the name of the module that contains the class. Our modules don't contain any test programs. So sometimes there is a main program at the very end, but here it's not the case. I want to indicate how you now work with these class-wide variables. So with any object, you have the selectors. So I chose here actually not really great names. CRE, that corresponds to the real part, the imaginary part, then the J part, and then the K part. So these are the four data attributes, the A, B, C, D of any quaternion. Of the class-wide variables, you see there is the count and the who. They are defined immediately after the documentation string, before the constructor. And in every constructor, whenever I have a new quaternion, I increase the count and I append the variable, I append the self to the who. The who is here initialized as a list. So that's how I get to the quaternions. So there is the string representation, there is the equality tests. So the equality test here is very basic. So this is between two quaternions. So again, this is not complete. You actually want to compare against the float, and you want to compare against any other type, so also against the complex number. So you can see that the complexity of defining complete classes can quickly turn into a lot of work. But this is then for the sake of having a very high cohesion. Everything that you want to do with quaternions should actually be defined by this class. Okay, so this is the essence of what I wanted to say. So I do not want to overload the materials in this lecture. Um, Object-oriented programming is very mm, is very complicated. So it's a more advanced tool motivated by the need for writing larger applications. But I hope that you can already see that even with um, limited amount of code, you can actually do some very cool things. So the quaternions may perhaps not appeal to you, but the counting of the flops is something that is quite useful at times. All right, so the most important slide of this lecture are, of course, the exercises. The main goal of the lectures is to invite you to experiment on your own. You will learn programming by doing. So the Python scripts will be made available on the course website, also the Jupyter notebooks. So the Jupyter notebooks are kind of a hybrid now, so they are perhaps better than. So I also have the flop sum, so this is another script. Um, the small scripts are actually now included in the narrative of the Jupyter notebooks. Okay, I will not stretch it, so I still have 5 minutes over. This is extremely good. I think I have illustrated the essence. So there is a self, there is an other, um, and in this way you can overload all the commonly known arithmetical and comparison operators when you make your own data types.